Okay, so we've taught up until this point mostly just general things about C++, about graphs, unit tests. We're going to start diving in now to the structure of the Rosetta code. So we're going to have a series of lectures entitled Library Structure. I guess, you know, there was one last night, I should hasten to add. So this is your second lecture on this topic. So we're just going to cover the utility, numeric, basic, and core libraries in this lecture. So it'll go pretty quick. Okay, so just as a quick outline here, I'm going to talk about a handful of classes within the utility library, vector1, vector0, the fixed size array, IZStream, and the tag class. I'm not going to say much about the utility heap or utility lexicographical iterator, but they're pretty sweet. And maybe at some point you'll decide to go back and look at these yourself. For the numeric library, I'm going to mention a few things about the XYZ vector, the XYZ matrix, the homogeneous transform, some useful functions that live in xyz.functions.hh, and the interpolation libraries. There's really useful code in the numeric deriv directory if you're calculating derivatives for some new energy term that maybe depend on angles or torsions. And then there's some useful code if you ever want to parse, say, like a text file and turn that into math. So if you want to have a text file that says 5 plus 3, and then actually compute 8 on the fly, then you can use some of the code that lives in the numeric expression parser subdirectory. Okay, in the basic library, I'm going to talk about, or this whole library is very fundamental code, but that has just a little bit of Rosetta influence. The numeric and utility libraries, those are like kind of Rosetta independent. There's nothing specific about proteins that governs how those libraries operate. In here in particular is the option system, tracers, and the resource manager. Core itself is divided into 5 sub-libraries. From core 1, I'm going to mention only types.hh, which was mentioned yesterday briefly by Rebecca. This is also where the core graph code lives. In core 2, I'm going to talk a little bit about the chemical and conformation layers, mentioning just a little bit about symmetry. I guess I'm not going to talk about core ID, but this lives in core 2 as well, or core kinematics. Rebecca will be talking more about the kinematics this evening. Core ID, I guess I can mention very briefly right now. Atom ID is basically a pair of integers. It's the integer representing which atom it is, and then which residue it comes from. So you could have an atom ID that's like 522, and that would represent the 5th atom on atom 22. DOF ID and torsion ID are somewhat similar, except that so they belong to a residue, and instead of identifying an atom, they identify a DOF that comes from that residue. From core 3, there's the two biggies are pose and scoring, and I'll talk just a little bit about some of the classes that live beneath these two directories. Core 4, I'm going to mention just a little bit about the packing subroutines that exist. I won't go into great detail on them. Jason, later in the week, will talk about the packer task and the task operations and residue selectors, which live beneath this directory. Also in core 4 is optimization. You had just a little bit of experience with that in lab 2 last night. So there's the atom tree minimizer. There's also the Cartesian minimizer that lives in this directory. And core 5 has not very much in it, but one thing that's there is the import pose directory. Also there is the core init function, which you guys have been calling, but indirectly through devel init. devel init calls protocols init, which calls core init, and you'll learn a little bit about why those init functions have to be there in the discussion on singletons and factories that Rebecca and Jason will be talking about later. Okay, so let's talk about the utility library. Vector1 you may have some experience with already. I believe we've encountered a few of them so far in the labs. They're templated on the thing that they hold. So if you went and looked in the declaration for the class, you'd see that it said something crazy like this: template, then angle bracket, class, t, then end angle bracket. And then it says class utility vector1. Sorry, it doesn't say utility vector, it just says vector1, and it lives in namespace utility. So it's class vector1, and then angle bracket t, close angle bracket. So the way this syntax works is that it says there's going to be this parameter that you have to specify for this class, and we're just going to label it with t. And so throughout the file, anytime the letter t stands alone by itself, it's going to be replaced by whatever thing that you specify elsewhere in the code. So if you wanted to use the utility vector1 of int, then the compiler is going to go through and it's going to replace all occurrences of the letter t with the word int. It'll do the same thing if you had size here instead. So you can have a utility vector1 of poses, or a utility vector1 of scoring functions. You can put whatever you want into this very generic class. We're not going to spend much time talking about the syntax of declaring templates or how you would write your own templates, but it is good to be familiar with how you can use templates. And even in your homeworks, you used integer lists, right? A standard list of int. What's different about the utility vector1, say from C-style arrays or even STL vectors, is that they index from 1. This is a carryover from Rosetta's Fortran days. There's lots of code that still is fairly complicated and involved, in which we haven't rewritten, that requires that we index from 1. 1 is also just a much better index. It's far more intuitive. 1 to n is meaningful to humans, and 0 to n minus 1 is not. And there's this great article that can be found. Maybe I'll look it up and forward for you guys later, but discussing the history of how we ended up with zero-based indexing, and it's not impressive. Like there was a language that was written for very old drum-based machines where you needed a zero-based index to make the compiler run a little bit more fast. It didn't make the code run more quickly. It made the compiler run more quickly. That language is long dead, and the drum machines are long gone. And so there's no reason to, necessarily hold ourselves to this idea that we should always index from 0. But in any case, utility vector1 indexes from 1. So it's unlike standard vector, which indexes from 0. So the valid index range for it is 1 up to n. And so when you look at for loops in Rosetta++, Rosetta 3, they usually have the index start equals to 1, and then the ending condition, or the middle condition in the for loop is the loop index is less than or equal to, say, total residue, or whatever the size of the vector is. So in contrast, if you were working with a standard vector, it goes from 0 to n minus 1. Okay, so the other great thing about utility vector1 is that it asserts the boundary conditions in its operator brackets. So when you treat a utility vector1 like a C array, when you try to use it with the bracket operator, it will actually go and make sure in debug mode that the index that you give it is within the range from 1 to n. If you give it 0, it'll throw an assertion error and say that this is out of the range of allowed values. If you give it n plus 1, it'll do the same thing. Or if you give it positive infinity or some very large number, it will catch it and stop you. Now, you might come back and say, oh, the standard vector does exactly the same thing. You just have to use the at method. And so instead of using like the bracket notation that's very common for arrays and which everyone uses, you just have to replace it with .at. And that'd be great if anyone were to ever use .at ever. But no one does. And so, and it makes the code just really ugly and hard to read. And so, yeah, this is just an unfortunate error in STL. And then again, the assertion, the boundary checks, they're removed in release build using the same ndebug compiler flag that standard vector uses as well. Okay, so in fact, underneath the hood, vector1 is derived from the same class that standard vector is derived from, and so and it has the same kinds of iterators and whatnot that standard vector provides. So it works with all the STL algorithms like sort. If you have some code that already exists that uses standard vectors, I'd recommend replacing the standard vectors with utility vector zeros. Utility vector zeros are just the same thing as utility vector ones, except they index from 0. The key thing is that they assert the boundary conditions. We'll actually have a lab tomorrow where you're going to see a boundary condition get violated in the GDB lab. It will trap in GDB, and it will be much faster for you to find this bug. And so being able to debug code easily is really useful. So go ahead and replace your standard vectors with vector zeros, or just use vector zeros in the first place, or just use vector ones since they're better. So another array is, this is to answer Alex's question from yesterday when he asked, is there any advantage of having an array declared on the stack versus declared on the heap? Which is kind of your question, maybe paraphrasing a little bit. And the big advantage of one declared on the stack is that you don't have to use new or delete to allocate it, so it allocates much more rapidly. And so this fixed size array, it gets declared on the stack, so it uses as its private data member the same style of array allocation, where it's a C-style array under the hood. And the size of it is given by one of the template parameters. So if you know that you're going to need an array of size 4, then you can use a fixed size array 1 and pass it 4 as one of the template parameters. And we use this a lot, say, in the Dunbrack library, where you know exactly how many chi dihedrals you have. You just need a small array to make the logic a lot easier. And so in the Rotimer library scratch space, it's just full of fixed size arrays of size. Actually, it's templated on the number of chi's in each of the residue types. So arginine has 4 and uses fixed size array of 4. And then it's also templated on the object that you're storing, so you can have fixed size array of 4 of integers, or fixed size array of size 4 of doubles. Again, it asserts boundary conditions with its operator bracket method, which a C-style array does not. C-style arrays have no idea when you're walking off the edge of them. And it has the iterator classes that you need in order to use it in algorithms like standard sort. Okay, so IZStream is a pretty useful class. It allows you to specify either a file like a text file or a gzipped text file that you can read from. And so when you try to initialize an IZStream, you'll give it, say, the name example.txt. It'll go and try to open example.txt. If it doesn't find an example.txt, it'll try again, looking for example.text.gz. And so if it can find the text.gz, then it'll just read from that. You can then pass this into any function that reads from an IO stream. And so this is just a much more general version of, say, standard if stream. It doesn't handle binary formatted data. So if you're working with that, then you can't use IZStream. Okay, so In tomorrow's lab, tomorrow's evening lab, you'll be using just a little bit of the XML parser code and the Rosetta scripts code. And that relies heavily on this class utility tag. Tag is a recursive data structure, so it has a vector of tag pointers. So it contains pointers to its instances of itself. And so you get a tree of ownership. So this is, say, an example of an XML file where you have this tag movers and a subtag set up for symmetry and another subtag report from to DB, which has all this data, and then report to DB. This one has two subtags here, and so you would have like an ownership graph of, let's say, I'll draw this on the board. So there's the movers top level tag, and then it has two children. One is a report to DB, and this one has its own pair of children. Anyway, so this would be represented as a set of 5 tag objects, and the topmost tag object has pointers to 2 more tag objects, which have pointers. One of which has pointers to 2 more tag objects beneath it. Jason will mention this. We'll give you some more examples tomorrow or Thursday. Okay, so what's in the numeric library? I'll talk about a couple classes here and then mention a few functions that are sort of hanging out within these two. Okay, so XYZ vector is a very useful class. It's great for representing the coordinates of points in 3 space. It's templated on the precision, so you want to give this as like either, usually you want to use real, core real, but if you want to specify your precision exactly, you would give it either float or double. You could, but I don't think it's a good idea, template it on integers or sizes if you wanted to represent points in discrete space. You just have to watch out for like division, right? Because I don't think the code would be happy with you, say if you had a, because integers aren't closed under division. Okay, so let's see, in core types there's this type def. I'll get to it in just a little bit, but numeric XYZ vector of double to vector. This is a little confusing because it might get confused with other vectors, but people do find this useful. And so if you want to talk about vectors, you can use this type def. So you talk about, if you were writing some code in protocols, you could talk about core : vector. That would refer to this type def. This class has, it's a really lengthy file. It has lots of useful numeric operations, including dot products and cross products. You can normalize vectors to unit length, and then it properly handles these cases where if you give it the 0 vector, it doesn't try to divide by 0. XYZ matrix is similarly templated on its precision, and it gives you basically a 3x3 matrix. Useful for representing rotation matrices, though my personal preferences for homogeneous transforms. You'll see XYZ matrix used in the stub class if you ever go digging around in core kinematics. Homogeneous transforms live here. They're, again, templated on their precision, so you can have a homogeneous transform of real or a homogeneous transform of float. They're 4x4 matrices where you have column vectors representing, say, 3 axes, an x, a y, and a z axis, and then a fourth vector, a fourth column representing a point in space where you have this coordinate frame. They're 4x4 matrices conceptually. In the code, they only use like a 4x3 or a 3x4 table of values. Because the bottom row is always represented this way. So 0 for the first, or zeros for vectors and 1s for coordinates. And so when you work with homogeneous coordinates, you would designate whether you're working with a vector or a point by setting either this value either to 0 or 1. What's nice about them is that they give you this easy way to convert back and forth between local and global coordinates. So if you have some coordinate f in space, and you've got some global coordinate q prime, and you want to know what is the local coordinate for q that satisfies this equality, then you can calculate this very easily by right multiplying both sides of this equation by the inverse of the homogeneous transform, so F inverse. And then that gives you Q equals F inverse times, I lost the Q prime here, Q prime. Homogeneous transform, it provides its own inverse function. I'm not asking you to compute the inverse for it. But this is a great way to very quickly get the local coordinate for points. And there's some other really nice properties. I can't remember if I'm going to talk about them. I'm not. One is that because they're matrices, they're associative. So if you have oh wait, no, I am. I remembered. Yeah, so you're using matrix multiplication for all your operations. They're invertible, they're associative. So if let's say you have two chains, chain A and chain B, and there's some rigid body transform that connects the two. And so you want to rotate chain B by some rotate about some certain axis, V, by a certain amount. And then translate along this new V prime by 0.3 angstroms, and then rotate along a fourth axis by another quantity. Then you could compute this by taking the rotation about V, a translation along V prime, and then did I do this wrong? Maybe we've gotten the order of this wrong. Translate along V prime. Yeah, I have the primes in the wrong location. So this should be V prime, and this should be rotation of V double prime. And then you do that for point P, and you do that, or point P sub I for all i's, for all atoms in chain B. So you compute one, you're going to rotate all of the atoms, or rotate and translate all the atoms in chain B by some amount. So what's convenient about associativity here is that you can you can multiply all of these together and compute this new transform that concatenates them all, or basically just multiplies them all, and then you have one homogeneous transform that results. And then you can just multiply this new transform times pi for all I. So you've reduced the number of computations that you'd have to do in this series of operations because of associativity. And so in this way, they're quite a bit faster than working with stubs, because with stubs, you're constantly moving points to the origin, rotating about some axis about the origin, then translating them back to where they were centered. And so all of those operations add up, and your code can be quite a lot faster with homogeneous transforms. And if you want to see some homogeneous transforms in action, I use them extensively in rewriting the matcher. And so if you use actgrep for HT real, you'll find lots of them. Okay, so xyz functions.hh, this file has quite a few really useful xyz and matrix operations, and also some trigonometric functions. Transpose multiply, angles, like that would take a matrix and a vector, transpose the matrix, multiply the vector, and then return a vector. I think this is an error here. Angle radians, you can compute the angle between 3 points. Dihedral radians will compute the dihedral between 4 points. Take a look through this file, because there's a lot of really great functions here. Okay, so now we're on to the basic library. Okay, so the basic library is where the command line option system lives. We have the tracers declared here. I don't think you've been introduced to them, or at least not all of you. And also here, and I'm not going to say very much about it, is the resource manager. Okay, so the option system It lives in basic/option/option.hh. I think you had to pound include this already last night. And this is where the global option object lives. So Jason on Friday will talk about our coding conventions, and one of them is that you really should not ever have global data, and you should try to minimize your interaction with global data to the greatest extent possible. And here's the best place to go to get some global data. Okay, so this option object, like literally its name is option. It holds all the data that's provided to the execution from the command line. You access it using option key objects. Last night you used the in-file s option key object. And it has the option class overload or has a bunch of different versions of the operator square bracket so that you can access it as if it were like an array or a standard map. These option key objects, they say the int option key is one class of option key. Int vector option key is a different class. This would give you, this would correspond to a command line option that you would give one integer for, like number of iterations. And this would give you data that the command line would provide, like how many iterations should I use in each cycle of ab initio, or something like that. Option keys get declared using this options Rosetta.py script. So you can add options to this script, and then when you run, see, there are a couple ways to run it. One is to compile, so that now it runs this option.py script by default every time it runs scans. And what that script does is auto-generate these .hh and .cc files, like in.optionkey.gen.hh. That's automatically generated from the option Rosetta.py file. So you don't want to go in and start editing this file yourself, because it'll get overwritten every time someone compiles. The key here, or the hint, is that it has gen in its name, so that you know it's been automatically created as opposed to something that someone wrote by hand. The option system is initialized through the devel-init call chain. So devel-init invokes protocols init, which invokes core init. And once you get to core init, then core init sets up the option system. Along the way, it's passing the argv and argc arguments up through here. And if you try to access the option system before core init gets called, it won't be ready, and it'll exit with a noisy message. One thing that I want to caution you on is that you should never ever try to write to the option system. The option system is read-only. If you do try to write to it, what you'll do is create a protocol that you can't run in a multi-threaded environment, because you can't have two threads competing for a single global resource, at least not to communicate sort of between sections of the protocol. Okay, so tracers are pretty cool. The tracer class is declared in tracer.hh. They're ways of sending output to the screen that are better than cout. Okay, I'll explain that in a minute. So the convention is that you name a tracer after the file that it lives in, with periods between the namespaces. So if you had a tracer that lived in etable.cc in source core scoring etable, then you would name your tracer core.scoring.etable.capital E etable. And so when you declare it, say down here, you'd say, I'm going to declare a new tracer, static tracer tr, and then you give it the name as the one argument in its constructor. So you would name it core.scoring.etable.etable. So every time somebody sends a message to the etable, for instance, like I'm initializing the etable, every time someone sends a message through the tracer is going to append its name to the line that appears on the output message. And so that means that as you're looking through a log file, you can tell where every message came from. You can see this message came from core scoring e-table. So I can go there to look for whatever problem I was having, like just before it crashed, for instance. So yeah, this means that, that log files become more greppable, and you can get just the data you want for a particular tracer from a log file using grep. The other nice thing that tracers, the other nice functionality they provide is that they're mutable. That is, you can mute them. This word has another meaning if you don't have the dash in the middle of it. And you can do that with this flag, -mute, and so you can give it a list of a whole bunch of tracers to mute. So you can mute core.chemical or protocols.match. And everything in sort of all the namespaces beneath the muted channel will be muted. So if you were to mute core.scoring, then that would also mute core.scoring.etable. If you want to mute everything in core, then you can say mute core. If you want to just mute everything, you can say mute all. Okay, the last part of the basic library I wanted to mention briefly was the resource manager. And what it is the system for managing per job load once data. So the easiest case to think of is ab initio, where as you're running an ab initio trajectory, you need to read the 3mers and the 9mers in order to insert those fragments into the pose that you're trying to change. And it takes like a minute to read the fragments in from the text file from which they're written. And so if you're going to run 100 ab initio jobs, then spending a minute on each job to then run like 30 seconds worth of ab initio is a waste of time. So we created the resource manager to address ab initio, and we haven't fixed ab initio yet. But the idea would be to replace a current shortcoming of ab initio, which is that when it runs, it sets up data at the very beginning of execution, and then it does so by reading from the command line, and then it runs for a very long time and exits. It means that you can't run ab initio through JD2, the new job distributor system, new as of 2009, and so there's some big drawbacks to that. It also means that you can only run one structure per job. And so if you wanted to run ab initio on 5 different structures, one job each, that's not even an option. You have to run that as 5 separate executions. So that's a bummer. The resource manager, the idea behind it is that each job will have some bit of data that you provide for it. So you would provide the fragments for each of the, say, 10,000 jobs that you want to run. They might be all the same fragment set. But every time that job gets started, the data that, like the ab initio protocol as it needed, the fragments, it would go to the resource manager and say, hey, give me the fragment set for my current job, I need that. The resource manager would say, oh yeah, I've already loaded these fragments, here, go ahead and use them. And it would let the ab initio code gets separated from the process of initializing the fragment data. One nice thing about the resource manager is it's exceptionally well documented, and I hope that can at least be a model for you of like how should you go and document your own system, and hopefully a model, an example, useful for you if you ever start using the resource manager. You'll know how to get to it. Okay, so that's like half of the libraries I was going to talk about, right? So we're almost done. All right, so all we have left is core. All right, so from core.1, I'm not going to tell you anything more about core graph. Types.hh, so it basically looks like this. So it declares this namespace core, begin parentheses, and then there's some type defs that now live in this namespace. So platform : size gets type def, to size. Type def double real, so now real lives in core, and that means double precision. So 64 bits for every continuously valued number that we represent. There are actually ways that you can compile Rosetta where this type def, instead of being double, is actually float. And that might be useful for you if you're seeing, say, cache limitations, where we're, say, using too much memory to store coordinates. And so you can, if you use double precision instead, then you can save on the coordinate costs. The danger there, and the reason why we use double precision in the first place, is that our minimization routines are more efficient in double precision. Requires fewer score function evaluations if you have higher precision on your calculations themselves. Also, there is this. I just thought I'd mention it. This packer energy, which lives in core as well, and this is type def to float in all cases. In the packer, it's a less numerically precise algorithm. There's we're not doing continuous motion for the most part, and so we don't have to be quite so precise in how we calculate scores for things that are very different from each other. And so we use lower precision in the packer. We also calculate dramatically more energies. Like you'll spend hundreds of megabytes, if you do it wrong at least, on packing jobs. And so you use half as many using floats here. Okay, so core.2. I'm going to tell you a little bit about residue type and residue, and then also class confirmation, and then connect that with the symmetry code. Okay, so one of the key parts of the restructuring that we had when writing Rosetta 3 was that we'd have this separate layer between this chemical layer, or separate layers between chemical and confirmation. And then confirmation would sort of look upwards towards data that was stored in the chemical layer. So you would abstractly specify something like a CH2 carbon or an alanine residue type in the chemical layer. And then when you went to go and instantiate a particular C beta for some residue, or maybe an alanine at residue 15 of a particular pose, then that would live in a confirmation layer. So this is like the platonic form of these atoms, the alanine and CH2, and this is the instantiated form, the concrete form. And the way this works is that there's pointers sort of up from the data in the confirmation layer to the chemical layer, and that's how, if you're dealing with, say, like a pose or a confirmation, it's able to provide you chemical information. So it has pointers back to the data that it needs. To a great extent, the two namespaces, core chemical and core confirmation, mirror each other. So there's the abstract, or not abstract, but the class type residue type that lives in core chemical is mirrored by the class residue in confirmation. And there's a correspondence between the data that lives in residue type to the data that lives in residue. So residue type will say, know the number of atoms that are in the residue type. And maybe it's got a vector of atom type information that describes the chemical information of these atoms. Rocco's head is shaking because these slides are old, so they may already be out of date. Yes, okay. Well, I'm going to tell you about it anyway, because I've got them. Okay, so maybe it's not a vector 1 anymore. Maybe it will become a vector 1 again. We'll see. So the key point is that the chemical information about the atoms, this will live in the chemical layer, is pointed to by, in this sort of correspondence, by the physical information. So there's a confirmation atom that lives in the confirmation layer, and there's a vector of atom information, and the entries in these two vectors correspond to each other. So that you can talk about, atom 10 from residue corresponds to atom type 10 in class residue type. So let's talk about residue type in a little bit more detail. Okay, so here's here's some extra data that residue type keeps around. So here's a utility vector 1 of size of the acceptor positions, and utility vector 1 of size of the positions that are the H positions that are polar. So these are atom indices that are represented in these vectors, and they represent the acceptors and the donors, and they're used by the hydrogen bond energy calculation. So when you're trying to figure out what are all the hydrogen bonds between a pair of residues, it's much faster to iterate across all the acceptors of one residue and all the donors of the other residue than it is to iterate across all the atoms and figure out whether each one is an acceptor or a donor. And so the residue type holds this information for the sake of speed in the hydrogen bond energy calculation.
So it iterates over possible acceptors?
Right. So, well, I mean, something is an acceptor either if it forms a hydrogen bond, and you say that's a hydrogen bond acceptor, or if it could form a hydrogen bond, in which case you could also say it. So these all could form hydrogen bonds. The acceptor posits could. They're not just the ones that do form hydrogen bonds. So those wouldn't be, they would be suddenly conformation dependent. Okay. So other information that's stored in residue type is basically a vector of vectors or table of path distance information. And so if you were to look into path distance I sub I sub j, that would tell you the number of chemical bonds that separate atoms I and j. And this is used in calculating the Leonard-Jones and Coulombic interaction energies, because you skip the interaction energies, you skip the calculation if I and j are within 2 or 3 chemical bonds, and then if they're 4 chemical bonds apart, then you say downweight them by a certain amount. And if they're greater than, or if they're 5 or greater, then you say that you calculate all the interaction energies. There's a graph theoretic algorithm called Warshall's algorithm that calculates these up front in n cubed time. It's kind of slow, but is faster than trying to calculate path distances in the middle of scoring. And you spend quite a lot more time scoring than you do actually constructing residue types. Each atom has a name, and each atom's name has to be unique within its residue type. You can't have 2 atoms that have the same name. And so you can, there's a vector, so you can get the atom name for position 5, for atom 5. And then there's also a map backwards from the strings to the indices for them. So if you have the string, in quotes, CA, right, you can go to the index that goes along with that atom. So that would be a map backwards. There are descriptions of how this residue can be connected with other residues, and that is in this form of residue connection objects. And it's used to, sorry, this animates. So, right, so stores information on how residues connect to other residues. For example, like alanine has 2 inter-residue connections, one at the N atom and one at the C atom. So alanine can form 2 chemical bonds to other residues, right? It's not too much of a surprise. Cysteine also has 2 inter-residue connections, but you might say, can't you form disulfide bonds? Couldn't you get a third? And you'd be right. But in order to do that, you'd actually need a different residue type, because now the information about how chemical bonds exist for this residue type are going to be different from, say, the canonical cysteine. So we have another one, CID, which is the disulfided version of cysteine, which has 3 inter-residue connections. There's a name for the residue type. Each residue type's name has to be unique within a residue type set, but there are different residue type sets that you could have. There's a FA standard residue type set. That's the one that it's the FA stands for full atom. That's the canonical one that people use when they load in poses from PDBs. There's also a centroid residue type set, and that's what you would use in ab initio folding or maybe even low resolution docking. So there's say, 2 alanines that usually get loaded into Rosetta, one in FA standard and one in centroid. Each residue type has an access pointer back to the residue type set that owns it. So it's an access pointer as opposed to an owning pointer, because it doesn't, you don't want to add an extra edge in the ownership diagram. You don't want to accidentally leak memory. Is there more to say about that? I think I also show that the residue type set has a map that goes from the name of each residue type, that's this thing here, to a pointer to it. And so you can ask for all the alanine residues, the alanine residue from the FA standard residue type set. And that's one way to get it. This back pointer is really useful if you're trying to redesign a structure and stay within the existing residue type set. So if you want to perform design on a centroid pose, you go to the centroid alanine that you have there, you ask for the residue type set that alanine corresponds to, and then you get all the other residue types that could be put at that position, all the, like the phenylalanine and the arginine residue types that you could design at that alanine position from the centroid residue type set. Okay, so the confirmation layer is mostly seen through class residue. There's a class atom I'll mention just a little bit about. The confirmation layer, so in particular, the residue class has a constant reference back to its type. So an instance of an alanine would have a reference to like the residue type alanine. And that way, it can answer you like how many hydrogen bond donor and acceptor atoms do I have without having to represent that data itself. It has a vector of atoms, as I mentioned before. So atom is a coordinate, so an XYZ coordinate. And it's also for rapid lookup in energy calculations, it actually stores a little bit of the chemical information. So there's a redundancy here. It stores the atom type as used by our the atom properties.txt file, and it has also an MM atom type, which is used to calculate the if you're also using an MM energy function. We have a couple of these implemented here that I'm not going to say any more about. Yeah. We should probably revisit that decision. At one point, we believed it would be slower to be incrementing and decrementing the reference counts, but I don't think we construct enough residues for that to continue to stay around. It certainly makes it more difficult for if you want to do like make sure that residue types persist as long as someone is using them, then that's quite a bit more complicated. It certainly isn't. We haven't excluded it on the basis of the ownership diagram. Like confirmation could own up towards residue type without any problems, because chemical is never going to own anything in confirmation. They're sort of separated out in that direction. It is faster to to get data out of a reference than out of a pointer, but that argument only says that we should have both a reference and a pointer, and that would be a workable solution. Okay, let's see. The next piece of data I want to point out is that each residue is associated with some sequence position, so it has an idea of what position it is in some context. without actually having some sort of, class residue does not need to exist in a context. It doesn't have to be a member of confirmation, even though confirmation does own some residues. It owns quite a few residues, but you can also create lots of residues outside of the confirmation class. And so, but there's some sort of context, some overarching position in which any residue is said to exist, and this is the sequence position in that. Sequence position starts at 1 and goes up to the total number of residues in the pose, I guess, in the context. We have other data to represent PDB info. The analog of the residue connection data that lives in the chemical layer is the connect map. And so this tells you exactly to whom you're chemically bonded. And so alanine 15 would have data in here saying, I'm chemically bonded to residue 16 at a particular residue connection port, like port 1. That allows, so the reason to have this as opposed to, say, pointers between residues, say having an explicit pointer from the residue in alanine 15 to the phenylalanine at position 16, is that you can put all kinds of different things at position 16 and say all of them are chemically bonded to residue 15, and have a whole bunch of different options for residue 15. All of them are chemically bonded to 16. Right? And this is what we do in the packer, when we actually create a whole bunch of residues to use as rotamers. Okay. I already said this. Excellent. Okay, so in addition to the XYZ coordinate information, the residue is also a receptacle for internal geometry. So it has a vector representing the chi dihedrals and the main chain torsions. This is so that they don't have to be looked up out of the atom tree every time you want to access this data. Okay, so class confirmation is, you can think of this as being the sum of a number of different things. It has a vector of residues. It has one residue object for every position in the structure. So if you have 105 residue protein, then you're going to have 105 residue objects. It provides read-only access to its residues. So you can ask a confirmation for residue 5, but it will give you a constant reference to that residue. And you cannot change this residue directly because it's constant. The compiler won't let you. So you might ask, why isn't the confirmation giving out non-const access? And the answer is that the confirmation's maintaining data integrity. So it's trying to keep data consistent between the residue object and between these two data members, the fold tree and the atom tree. So the fold tree and atom tree, they represent the kinematics of the system. And when you say, I'm going to change the internal geometries, I'm going to change the phi psi and omega dihedrals as something in the middle of a protein, the atom tree writes down, okay, the phi psi and omega have changed at these residues. But it doesn't update the Euclidean coordinates immediately. It waits until you're done saying all the things that are going to change. And that way you can specify, say, all the 9mers, or all the changes that would go along with doing a 9mer fragment insertion in a single go. So you call set phi, set psi for a whole bunch of different positions, and it doesn't do a refold in the middle. It doesn't recompute these coordinates. It waits. And then what happens is you go to ask for the coordinates of any residue, and it says, okay, I've got some data that's been outstanding. It's time for me to go and perform a this lazy update. So it does this just-in-time update of the coordinates for the residue. It writes down the coordinates in the residue object, and then it hands you back now a constant version of that residue. And so what's going on here behind the scenes is that, in fact, the confirmation has marked this piece of data as mutable so that it can change it inside of a constant function. We're going to talk a little bit more about constant tomorrow, but it means if this is constant, then when you invoke it on the confirmation, it means the confirmation isn't going to change. But the confirmation says, okay, I told you I'm not going to change, but I'm going to change. I'm going to change this in particular. So it's going to update the data that's inside this residues object, this residues array. It's going to update their coordinates based on the queued set of internal degree of freedom changes that you've made from your fragment insertion. So the way you actually go ahead and change a residues confirmation is using these setters. The confirmation lets you set a DOF, where you give it a DOF ID and the new value, or set a torsion by giving a torsion ID and the value, or setting a coordinate by giving an atom ID and then a new coordinate. And then the confirmation watches you while you do this, right? It's keeping track of the changes that you're making. And it's going to know that the next time that you try to get this data, it's going to have to migrate some of that data into the appropriate places. So this is one of like the most beautiful parts of encapsulation, is that you can maintain data integrity, you can provide guarantees that no one will ever get data that's out of date, while making the interface really simple, right? I mean, you just ask for residue 5 and it performs a really complicated calculation. And without requiring you to know in the background, maybe I have to do this refold before I ask for the coordinates, or they might be out of date. And that would have like this consequence of either making the code more complicated, or it would have the consequence of if you just call refold over and over again, in anticipation that something might have, that there might have been a internal degree of freedom change, that you would actually slow down the code, right? So the code is optimally fast, it is optimally simple, and the reason for it is that it prevents you from accessing, or it controls the way that you access and change the data that it holds. Okay, one more thing to point out about confirmation is that it's meant to be derived from. So the set DOF, set torsion, and set XYZ are all virtual functions. And this paves way for the symmetric confirmation class. So it overrides the behavior of set DOF, set torsion, and set XYZ. And it does so with the help of this symmetry info object. Okay, so if I have a symmetric structure, let's say I've got a threemer, the way the symmetric confirmation works is that it's going to model, it's going to let you change things in chain A, in what's usually called the asymmetric unit. And then it's going to apply the identical set of changes to chains B and C. So if I have residue I in chain A, then it figures out, and I make a modification to residue I, and it figures out how to make that same modification to residue I prime from chain B. And then you can't see it, but residue I double prime from chain C.
Sorry.
Yeah.
Can you say again what being virtual has to do with that?
Sure. So the pose will hand you a reference to its confirmation object. And then you can call a function like set DOF on this reference that's returned. Sorry, I should repeat the question. The question was, what does these functions being virtual have to do with it? And the answer is that they let code be agnostic as to whether they're working with a confirmation object or a symmetric confirmation object. So the pose will hand you a reference to a confirmation, and you can call a function set DOF of this confirmation. You can call its method. And you don't have to think about, as you're writing this code, whether you're working with a symmetric confirmation or regular confirmation, because the right function will be called. Like it's going to invoke, if you have a symmetric confirmation, then behind the scenes, the compiler will ensure that the symmetric confirmation's set DOF function is going to be called. Okay, so I mentioned earlier that the helper class here is symmetry info. So what it holds is a set of information in these cloned type def. So this is a vector one of size, call them clones, and there's a map between each residue in the asymmetric unit to the list of all of the other residues that are clones of it. So for residue I in chain A, it would list I and I double prime as the symmetric clones of residue I. And there's similarly jump clones, which is just a little ahead of schedule, but we'll be talking about jumps this afternoon with a fold tree and in this evening's exercise. They represent rigid body transformations in space. And so here I've got two jumps represented as these red arrows, and therefore the asymmetric unit. And the symmetric clones, the jump clones for this would be this clone and that clone. And then for this jump, it would be that jump and that jump are its jump clones. And these, so when you change the rigid body degree of freedom here, when you change this jump, the same rigid body transform is applied to these two jumps as well. And so if you imagine, if this is the axis about the center and this is your A subunit, your asymmetric unit, and you pull it away from the axis by changing this linear transform from the center of the axis to here, if you extend this further and pull the subunit away, then similarly the chain B will be slid away and chain C will be slid away. So it'll expand outwards, kind of like the part of the head of a drill that grabs the bit. Kind of spirals outwards. Okay, so now we're going to move on into core 3. Class pose, you've seen a little bit of already. It contains quite a bit of stuff, but primarily it contains a confirmation object and an energies object. It stores an owning pointer to a confirmation class. And so you can replace a confirmation object with a symmetric confirmation object. So you can make a symmetric pose by changing out its confirmation object. There's an analogous set of changes you need to make to the energies object. So instead of an energies class, you would need a symmetric energies class to be used here if you're going to use a symmetric pose. So the pose, I guess I like to think of the primary purpose that the pose serves is to communicate changes from the confirmation object to the energies object, so that after you've set the phi psi angles for, say, a stretch of residues in the center of your protein and triggered a downstream propagation of confirmation and change, that information gets relayed to the energies object. Okay, so like I said, there's a few more things that the pose contains. It contains a constraint set, which is an object for holding constraints. We'll talk about constraints more on Friday. It holds this very low-level data structure called a data cache. The data cache is an array of pointers to things, pointers that are derived from reference count. Actually, they're derived from cacheable data. So it's possible to store arbitrarily complicated data in a pose. Since the pose is usually what gets passed, say, from mover to mover or around in a protocol, it's the pose that goes from one function to the next. It's convenient to embed data into the pose, and we do so through the data cache. See, this array, this data cache is basically an array. It uses an enumeration in the cacheable data type so that you can sort of register a position in this array for use in a particular class. And because it's an array, it has constant time lookup access, which is really useful if you're trying to calculate energies based on stuff cached in this data cache. The hydrogen bond evaluation machinery uses the data cache this way, so it records information about the number of neighbors for each position and whether there are existing hydrogen bonds. I'm not going to get into the fine-grained details, but in any case, the hydrogen bond energy needs to get data out of the data cache every time you evaluate the residue pair information for a pair of residues that are interacting. And so that's why this has to be fast. If you put data in the data cache, though, you watch out because it gets cloned every time you do a post-copy operation. And so if it's a lot of data, if cloning is a slow operation, then this can slow down a protocol. So getting into scoring, there's a large enumeration here, score type, which has something like 250 entries at this point. It's a pretty large number, and the last entry in this enumeration is n score types. The score type enumeration is paired with this energy map class, which is basically an array, and this array is keyed so that it has as many entries in it as there are score types. The purpose of this array is so that you can have an energy term describe several different, so something that calculates an energy, like the E-table energy, that class, can return multiple score terms, say, in one go. So you can return both the FA attractive and the FA repulsive term, as well as the FA sol term, all at once, without three separate invocations. So it has to communicate to the code that calls it through this energy map class. So you'll see these all over the place. They're just a place where you can write down energies, typically unweighted energies. It's also where you write down the weights for the energies, where the score function does. Okay, so class energies, this is a data member of class pose. So pose has an owning pointer to an object of type energies. It has a vector of energy maps, one for each position in the pose, representing the one-body energies. So these are all the interaction energies that sort of a residue has in vacuum, kind of by itself. And then there's an energy graph class that's stored in here that holds the residue pair energies. So after you've calculated, so as you're iterating across all the adjacent pairs of residues, and you calculate the interaction energy, you write down what energy you calculated into edges in the energy graph. I'm going to skip some of the details that I thought I might talk about. Energy graph, it derives from class graph, as I mentioned this morning. It does a pretty nifty thing when it allocates edges by using this class. It's just so I call it boost unordered object pool. It's a variant on the boost object pool. It's not actually part of a boost standard. For those of you watching at home, you won't find this in Boost. It's just a slight edit of the Boost code that I've added to Rosetta that lets you allocate blocks of edges all at once. And then when you allocate new edges, if you've got space in an existing block, then you can just pull one of those pieces of one of those entries in that block out and use that as your edge. So it'll let you avoid new and delete when you're doing edge insertion and deletion, which tends to be some of the slowest parts of, say, a pose copy operation. It also keeps an array pool, which is just a pool but for arrays. Usually the purpose of this array pool is so that each edge can keep like 5 entries, because usually there's only a few residue pair terms that are on at any one point in time. And that makes us go much more quickly. That is, edge insertion and deletion goes much more quickly because of this array pool. But I'm not going to go into any more detail on that. Okay, so what I did want to get into, though, is the energy method class hierarchy. So the base class is class energy method, and then from that there are 3 derived classes. There's a one-body energy, a two-body energy, and a whole structure energy. And so these classes are responsible for calculating the kinds of terms that you would expect based on their names. So here's energy method up here. Here's a one-body energy method, a two-body energy method, and a whole structure energy method. And then splitting off between, say, the one-body energy methods, you have the context-independent one-body energies and the context-dependent one-body energies. The context-independent one-body energies, those don't depend on, so let me just say, context-dependent means for a particular residue or for a particular pair of residues, in order to evaluate their interaction energy, you sort of have to take into account what's going on at all the surrounding positions. So in many ways, context-dependent pair energies are not at all pairwise energies because they depend on a large pose. They're almost like whole structure energies. But for the sake of expediting packing calculations, you can kind of treat them as if the context is fixed, say, just as you're swapping out side chains in the middle of packing. And so you can actually evaluate these the same way you evaluate context-independent one-body energies in the packer. For an example, in the hydrogen bond energy calculation, I guess historically, the interaction energy between I and J depends on the number of neighbors each residue has. And so hydrogen bonds get stronger and stronger the more buried each residue becomes. So the split here between context-independent and context-dependent one-body energies reflects the differing behaviors that so the score function needs to be able to treat terms that differ in their context dependency separately, and so there's a separation in the classes here. Would somebody mind pouring me a glass of water? I'm beginning to fade here. Okay, so for two-body energies, there's a split between short-range two-body energies and long-range two-body energies, which each individually split between context-independent and dependent versions of them. And I'll talk about those in just a moment. And the way I've color-coded this here is that the grayed out boxes represent the base classes that are meant to be derived from directly by concrete energy methods, by ones that will actually be used in evaluating the score. None of these are actually used. You can't actually instantiate any one of these classes because they just specify kind of how they're to be treated, but not what they do. Okay, so for two-body energies, this distinction between short range and long range, thank you, Rocco, is for short range two-body energies, there's some cutoff, there exists some cutoff D, such that if all heavy atoms on residue I are further than D distance away from all heavy atoms on residue J, then you can guarantee that there is the interaction energy between I and J is 0. So you can avoid a calculation of the pair energies between them. And so short-range two-body energies, one of the key things that they do is provide this distance cutoff D that's then used by the score function and by the packer and by the other energy method consumers. For long-range two-body energies, there's just simply no such cutoff. It doesn't mean necessarily that all residue pairs are going to have some interaction energy. It just means that there's no distance cutoff that you can use to decide which residue pairs interact. So the way these end up getting treated by the score function is that the short-range two-body energies, their interaction energies get stored in the energy graph. So as the score function is iterating across the neighbors that it finds, it invokes the short-range, the context-independent and the context-dependent short-range two-body energies to evaluate the residue pairs that, say, fall within that range, the energy for that residue pair. And they are effectively relieved of the responsibility for having to evaluate the energies themselves. In contrast, the long-range two-body energies, they have to provide their own data structures, their own containers in which to store the energies that they calculate. And that these containers tell the score function, or they tell the packer, or anyone else who cares to listen, which residue pairs have a non-zero interaction energy. So an example of, say, a short-range two-body energy would be, say, the Leonard-Jones energy. So there's some cutoff distance, usually at 6. Sometimes people play with 9. And beyond that, there's no pair interaction energy calculated. And then when you calculate the Leonard-Jones energies, they're stored in the energy graph. In contrast, there's the constraint energies that could be at arbitrarily long distances. And so the constraint energy has to provide a constraint graph that says, I have a constraint between residue 10 and residue 50, and this constraint needs to get evaluated regardless of how far apart residues 10 and 50 become. You wouldn't want to accidentally stop evaluating the constraint energy between residues 10 and 50 if they got far enough apart, right? If they got over 50 angstroms apart, you're like, it's probably an interaction energy of 0, especially if you want them to be right next to each other. You don't want to bias your search to search for the opposite, that is, force residues 5 and 50 as far apart as you can, because then the interaction energy will be 0, as opposed to trying to jam them together when it's really difficult, and so the constraint energy is probably non-zero. That would be defeating the purpose. And so that's why the long-range two-body energies have to provide their own mechanism of telling consumers who has interaction energies. So two-body energies, they all define this virtual function, residue pair energy. This function takes a pose that serves as the context, a score function, which is what's being used to evaluate the energy, a pair of residues, residue 1 and residue 2, and an energy map reference, which is used to write down the result. And all the two-body energies that exist, they all implement this same version of the residue pair energy function. So the score function, this is, I've got a bullet, it's either on this slide or the next slide, but I'll make sure to remember it. The score function is now a container for energy methods. So it has an energy map representing the weights. So you would have in this map for, say, the Teleris 2013 score function, it would say FA adder gets a weight of 0.8. And each of the non-zero entries would be written down in this energy map. All the zero entries would be written down as well. Then it has a set of lists. These are all type defs. So the CI2B methods is a type def for a standard list of context-independent two-body energy owning pointer. And so it has a list of methods pointing to all of these. It's got a list for each of the classes of these 7 grade boxes that I showed earlier. Okay, so yeah. So the point is that the score function is sort of energy method consumer number 1. So you'll see the second one in just a bit. But it doesn't really care what term you're evaluating. You give it energy methods and a pose, and it will go and just calculate the scores. And the big advantage of this is that it's got a fairly complicated algorithm. I described it to you in the last lecture. I'm going to return to it in the next slide. But it's a little bit involved, right? And so if every time someone wanted to add a new score term that they were interested in maybe testing out, if every time they wanted to add such a method, they would have to go in and change the score function. If that were the way we'd set this up, then the score function would be in shambles. We would be constantly having it break. We would never be sure what the actual score for ubiquitin was, and it would be a nightmare. And because of the use of virtual functions and abstract base classes, the score function class has had very little change in it in the past almost 7 years now. Okay, so returning to the algorithm that I described this morning, how do you rescore a pose? I'm just going to give it in a little bit more detail. So the first step is you drop edges from the energy graph on the basis of the domain map for pairs of residues that have moved with respect to each other. Those are the old edges. Their energies are out of date. You go and do neighbor detection using the distance, the maximum distance threshold from the short-range two-body energies. So if you have 5 different short-range two-body energies, and the longest reaching of them has a cutoff of 7 angstroms, then that's the cutoff you use to do your neighbor detection. And then you iterate across this point graph and add new edges to the energy graph, also using the coloring represented in the domain map as input. All right, so steps 1, 2, and 3 we just covered. Step 4 is now you're going to iterate across the energy graph. You're going to rescore all the context-dependent two-body energies. The reason for this being that you can't prove between score invocation to score invocation that the context has not changed in the pose. There's no general way to describe that. So all the context-dependent two-body energies get recalculated at every step. Then you look at the edges. So in particular, if you have an edge between I and J, and the 2 residues it connects have different colorings in the domain map, then you rescore the context-independent two-body energies. So the Leonard-Jones energy, for instance, gets rescored only if 2 residues have different colorings in the domain map. And then when you have both of these, then you can store those residue pair energies on an edge, the new edge in the energy graph, or on the existing edge, if in the case that they have the same coloring. Okay, then you're going to iterate across all residues, score the context-dependent one-body energies. You can't prove that the context hasn't changed, and so the one-body energies have to be recalculated. And then you look at the residues that have had internal DOF changes. So let's say you set phi or set chi on a particular residue, then it's had an internal DOF change. And for those, then you have to rescore the context-independent one-body changes. So in my example that I've been using of a fragment insertion in the center of a pose, you only rescore the context-independent one-body energies for the residues at the fragment that got inserted. Then you iterate across all the long-range two-body energies, and you ask each long-range two-body energy for an energy container, and then you iterate across all the edges in the energy container. Energy containers are more or less graphs. They provide iterators so you can iterate across pairs of residues. And for every pair of residues, you score it if the energy term is if the long-range two-body energy term is context dependence, or if I and J have moved with respect to each other and it's context independent. And then once you finish that, then you can evaluate the whole structure energies. What are whole structure energies? Say the contact order energy is a whole structure energy. The radius of gyration energy is a whole structure energy. If you want to fold based on RMSD, then the RMSD energy is a whole structure energy. And it requires an entire pose. Awesome. How am I doing on time?
3 o'clock.
Does that mean I'm 15 minutes over?
Yeah.
Okay. All right. Well, then I'm not going to say very much about Core 4. So Core 4 has the packer and the optimizer or optimization, pack and optimization. In Lab 2, you called pack rotamers. There are a couple of variations on it that are all fairly similar. There's rotamer trials, which is optimize one side chain at a time. Pack rotamers optimize all side chains at once. Then there are the continuous variants of it. So RT-min, which you optimize one side chain at a time, and then you minimize each rotamer before you figure out which one is the lowest energy rotamer. In min-pack, you optimize all side chains at once, and every time you make a rotamer substitution, you run a brief minimization on the newly placed rotamer. This is energy method consumer number 2. So it takes apart the score function. It uses the interfaces that are provided by the one-body and two-body energies to calculate only the parts of the energy function that have changed for any rotamer substitution. Except for the somewhat newer flavors of this, the code that lives in core pack is mostly unchanged over the past 7 or so years. In core 4, there's also the optimization. There's the atom tree minimizer, which you've used last night. There's also the Cartesian minimizer. The difference has to do with the number of degrees of freedom in the system. The atom tree minimizer mostly optimizes dihedrals, just usually phi psi omega and the chi angles along the backbone. And it relies on the energy methods to calculate F1 and F2 derivative vectors. This will be the subject of the last lab on Friday, the last lecture on Friday. So I won't say anything more about them now. The Cartesian minimizer has several more DOFs. It has 3 DOFs per atom, one for X, one for Y, and one for Z, right? And so this makes it massively more expensive. Fortunately for our implementation purposes, it can use the F2 derivative vector, and so we don't have to implement separate logic for calculating F1 and F2 derivative vectors for the atom tree minimizer, or derivative vectors or derivatives at all for these 2 minimization schemes. There's a minimizer class, which is actual implementation of these abstract minimization routines. These two are kind of interfaces to this code. They're not minimizers in the proper form. And what they take are multifuncs. And a multifunc defines these 2 virtual functions. Func, which takes a vector of reals named DOFs. So given an assignment of DOFs, it calculates a real value. So these could be the phi psi omega and chi dihedrals all along the backbone for all the positions. And then it would evaluate the score function and return that to the minimizer. And defunc is then the same assignment of DOFs, and instead it writes down the partial derivatives of each of those DOFs with respect to the score function. It's nice to know that this is here because if you have some arbitrary function you're interested in minimizing, you can minimize it by just creating a new multifunc derived class. So there's an atom tree multifunc and there's a Cartesian multifunc, and they derive from this multifunc class. I use this code in weight optimization, where you try to minimize in weight space given a set of input structures. Anytime you want to advance, just fine. Oh, it's the last one. Excellent. I was like, well, if Google's not going to advance it, then I may as well keep talking. Thank you for stopping me. All right, any questions? Jared?
Just a quick question on the, 2 slides before the variations of packing. And has that been, I was asking this to, I think, Patrick Conway, Frank Lyle, whether all 4 of them have been benchmarked as to accuracy versus the time it takes to run them for multiple. I'm always confused whether I should use rotamer trials, rotamers, or min pack in my protocol.
Yeah, that's a tough question. Or rather, I don't know the answer to that question. I can tell you it's probably going to be domain specific, right? So that, for instance, in the old version of Relax, in classic Relax, as opposed to the flavor we use now called Fast Relax, oh, and I just remembered, I forgot to repeat the question. So the question was, have these 4 flavors been benchmarked for their accuracy versus their running time? Okay, so the answer back to that is that in Cartesian Relax, classic Relax, I believe you just ran rotamer trials in every step, as opposed to doing pack rotamers. And I think the justification for this was that the structure is changing very little between each perturbation, each iteration, and so why repack the whole thing? Let's see. I can tell you that for accuracy, Matt and I are working on a paper that's not quite done, which at least gives accuracy on a bunch of different score functions for each of these 4 techniques. We're not reporting the running time, but maybe Matt can tell you what the running time is.